In this video, in section 13.4, we're going to look at question number 5. Here it says that the table below shows values for a function f. Use the table to approximate the derivatives fx at 2, 3, fy at 2.4, 3.3, fxx at 2, 3, fxy at 2, 3, and then finally fyx at 2, 3. Okay, and here's our table of values. Now, as far as reading the table, okay, notice this row here, this refers to the x inputs, so 2, 2.1, 2.2, these numbers refer to x, and then this column here is referring to the y. So for example, if I'm looking at fx at 2, 3, right, the function value at 2, 3 would be right here. It would be our 4.296, okay? So here is the idea, right? If I'm going to look at fx of 2, 3, what I want to do is imagine, and I've drawn a little cross section here just to help us visualize this, right? Here I am at 2, 3, and from the table, right, we know we're at an altitude of 4.296. And to measure the x derivative, well, I want to now take a step forward in the positive x direction. And so down here on the table, what I'm going to be looking at, right, is taking a step forward in the x direction. So I want to look at these two entries right here in my table, okay? So over here, right, I'm going to increase my x to 2.1, but y is being held constant for the fx derivative, right? So the height there at 2.1 comma 3, that's up here at 4.326. So I'm going to be, say, up here. Okay, so now our curve is going to be doing, you know, something between these points, increasing like this, presumably. Okay, and what we're going to do to approximate the slope of the tangent at 2, 3 is just simply measure the slope of this secant line, right? So we're going to look at this slope right here, okay? And what does that amount to? Well, it's going to amount to just taking the difference in these two z values, right, from our table. So up here, this is going to be 4.326 minus the 4.296. Okay, that's going to give us this vertical change, right, in z, and that comes out to just be 0.03, by the way. And then we're going to divide that by what? Well, the change in x, our run here, and that's just a difference of 0.1 here as we go from one point to the next. Okay, cool. So we're going to do 0.03 divided by 0.1. This would come out to a value of 0.3. So our approximation to fx, and maybe just to emphasize here, I'll say, you know, this is approximately equal to, at 2, 3 here would be 0.3. All right. Now fy at 2.4, 3.3, really just the same idea. Now we're looking where in our table? Well, x is 2.4 and y is 3.3. So right here, right, would be our z height at that point. And up here on the cross-sectional view, I've gone ahead and put that in. So 2.4, 3.3, our z heights are 5.284. And now, since this is a y derivative, I want to take a step forward in the y direction, right? And so I'm going to take a step forward in the y, so x is constant, so it's still going to be 2.4, and then our y will bump up from 3.3 to 3.4, and we now want to know the z height at that point. So in other words, down here on the table, right, we are moving down, right? We're looking at these 2 points now. Okay, and so the height up there is 5.406. So 5.406. Okay, great. So now to find the slope between these, which is going to give us an approximation, we're going to just do the difference in the z's, so 5.406 minus 5.284, and then we're going to divide that by the horizontal change, which again is just a 0.1. And this vertical change here happens to be 0.122. So dividing that by 0.1, we'd get what, 1.22? This would be our approximation to the y derivative of our function evaluated at 2.4, 3.3. All right, great. So now let's check out the second derivatives, right? And as we know, second derivatives a little bit more intense. Okay, so let's check out fxx at 2, 3. Well, remember, this is measuring how our x slope changes as we march forward in the x direction. Okay, so I've gone ahead and just drawn a little cross-sectional view here. Okay, here we are at 2, 3, our base point, which we know from the table has an altitude of 4.296. Now if I march forward, right, 1/10 of a unit in the x direction, that's going to put me at 2.1, 3, just like in the last cross-sectional view we had. And we know the height there is 4.326. But then what I want to know, right, is, okay, I measure that x slope, but then what if I go forward a little bit more in the positive x and then measure this slope? How do those two slopes compare? That's what fxx is really measuring, right? So here what I can do is say, well, I'm going to measure this slope right here, and I'll call this, say, mx1. And we already computed that. That was our 0.3. Now what I can do is measure this slope from here to here. Okay, and to do that, what I'm going to do is, of course, same thing, just subtract our z coordinates, and then I'm going to divide by the run, which is still just 0.1. And when you do that, it turns out you get 1.16. So our second x slope here would be 1.16. I'll let you check the values there. Okay, and so then what are we going to do? Well, we want to know, right, how does this thing change as we move from here to here? Okay, from this slope to this slope. Okay, so here's what we're going to look at. We got 1.16 minus that initial slope, which is going to be 0.3. And we're measuring, right, how this slope changes with respect to x, right? And so here, our horizontal change is, again, just 1/10. Okay? So one comment here, I mean, I can compute this out. And what do you come out with? 8.6. This would be our approximation to the xx derivative. Okay, but yeah, what I wanted to point out here is that in the table, what are we really looking at? So we're at 2, 3. So we computed in blue here, right, the slope from these 2 points. And then what we did for orange is we computed this slope here. Okay, and then we're looking at, right, the rate at which the slope is changing. So we then took the difference in those slopes and divided by the change in x, and that is how we're getting that 8.6. Okay, very good. And then on to the last one. This is the xy derivative at 2, 3. Okay, so again, just remember this is the fx derivative, and then we're going to take the y derivative of that and then evaluate at 2, 3. Okay. Now, I've drawn here, like we saw in the last video with the contour diagram. Okay, I've drawn 2 cross sections now. And notice now there's going to be some movement in the y direction, and then we're going to look at how the x slopes change. Okay, so here what I'm looking at is, first, here we are at the point 2, 3. Okay, and then if I say measure the slope in the x direction, right, from 2, 3 to 2.13, okay, this is just going to be this same blue slope up here, okay? This slope right there, I'll call it our mx1, this is going to be still 0.3, okay? And that corresponds to just these these 2 points right here on our table. But now what we're doing, right, is we're going to take a step forward, not in the x direction like it did here. We're going to take a step here in the y direction, right? Because we're seeing how my x slopes change as I move in the positive y direction. So that's going to look like this. It's going to consider these two now. Okay, so in other words, if I take a step over, and I'm now going to look at these z heights, the 4.385 and the 4.465, what is this slope going to be? And this, I'll call this mx2, okay? I'll go ahead and let you verify. So if you take the difference in these z heights and divide by the run of 0.1, it turns out you get 0.8, okay? And so now what is the xy mixed partial measuring? It's saying, right, okay, how did these two slopes compare, right, with as a rate measured against this change in y, which again is 0.1. So we're going to get what? 0.8 minus our 0.3. And then I'm going to divide that by the change in y, which is 0.1. And this comes out to be 5. Okay? All right. Now, for the last derivative, the fyx derivative at 2, 3, Clairaut's theorem says that these two things, right, are equal. Now, since we are approximating, right, we're not necessarily guaranteed that the approximations are going to come out to be exactly the same. Turns out that in this case, even the approximations are exactly the same. And so I'm going to leave it to you. It's a good exercise to check this. Okay, see if you can come up with the fyx derivative using this very same idea, and you're going to get that approximation still to come out to be 5. All right, that's going to do it for this problem.